today chemical equilibrium, ionic equilibrium, remaining parts we are going to complete. So from ionic equilibrium, what are the left parts? Ionic equilibrium. So common ion effect we already completed, and third is yes, buffer solution. And third will be salt hydrolysis. Then fourth will be solubility and solubility product. So these things we will discuss one by one. So this is completed, so three things is left. So let's start with buffer solutions. Buffer solution. Okay. So buffer solutions means what? A solution in which if we add little amount of acid or base, pH of the solutions will remain nearly same. So that is what is called buffer solutions. Okay, so buffer solutions, what is that? How to prepare buffer solution? So preparation of buffer solution, we say that you should have one weak acid plus salt, which is having weak acid and strong base. Then we can prepare the buffer solutions. Or if we have the weak base, then we have the salt, which is the weak base and strong acid. Then we can prepare the buffer solution. Let's say if I say weak acids, so let's say 3COH plus any salts which is weak acid and weak base. So like CH3 CONA, because this is salt. These salts came from, like if we said CH3COH plus NOH, this is weak acid, this is strong base, and if you react it, then what you are going to get? CH3CONA salt plus water. So this salt is come from what? Weak acid and strong base. That's what it says, that if weak acid and strong base, if you do, then and you will get this salt, and whenever you will react that weak acid with weak acid and strong base, then we get the buffer solution. Buffer solutions. Not that weak acid, instead of weak acid, if you take strong acid plus strong acid weak base, then buffer solution not able to prepare. Why? Because this buffer solution. This is the applications of common ion effect. So in common ion effect we see that any weak acid is there, with that one strong electrolyte is present. Any weak electrolytes, with that any strong electrolytes is there, and both having the common ions. That is the what common ion effect says. So we need that one weak acid, need one weak components, and with that weak components we have the strongs and both have the common ions. Then that is the common ion effect. So for this buffer solution also we need one weak component, with that one salt is needed. So if you take the strong, then the buffer solution will not prepare. Okay, so this is the conditions of preparations of buffer solutions. And indirectly where they will says that indirectly not this is the conditions of preparations of buffer solutions. This is the only conditions of synthesis of buffer solutions. If this condition is satisfied, then buffer solutions will prepare. Other than this condition, buffer solutions will not prepare. So indirectly they may say that they may give like CH3 COH plus NaOH. Is it possible to prepare buffer solutions? Yes, because you have the weak acid and you have the strong base. Whenever you react it, then this CH3CO Na plus water, this weak acid strong base salt has prepared, and this uh, salts, weak acid salt, strong base salts. After that, what will do that you will make this CH3CO and react with CH3COH. Then you can prepare the buffer solution. And condition is only that this should have 0.2 molar, that 0.1 molar, so that after reactions of this, this should be left. Whenever you use this one, then this also 0.1 molar has prepared. So from here only 0.1 molar is prepared. So initially this was 0.2 molar, so 0.1 molar has left. So from 0.2, 0.1 molar has left, that 0.1 molar again we use. This is 0.1 molar, again use 0.1 molar. So this is, you have to take 0.2 molar, this should be excess. Then this remaining part is left. So again after synthesis of this we will react with this one which is excess. So then we will prepare the buffer solutions. Standardly they wants to say that give this one and they like to prepare. So ultimately you are getting these conditions. This is weak acid, strong base, this is weak acid. So ultimately if you get this condition, then buffer solution will be prepared. Similarly for if I say NH4OH similarly if we say that NH4OH, that is weak base, plus NH4Cl, whenever you react it, this is weak base strong acid, because NH4Cl, how will you get? Whenever you react NH4OH plus HCl, this is weak base strong acid, then what will you get? NH4Cl, this is weak base strong acid plus water. So this one comes from weak base strong acid, and then you will get the buffer solutions. Okay, so condition is weak base strong acids. So indirectly they can ask that Directly they say that NH power OH plus HCl. Then can you prepare that vapor solutions? Yes. Whenever you react it, then you will get NH per Cl plus water. And if this is 0.2 molar given and 0.1 molar, then molar initially 0 0 and T equal to T equilibrium. Whatever this 0.1 molar is used and this is consumed and 0.1 molar is prepared. Yes. After that, what you do in the solutions? In the solution, this is left. So now what we will do? We will use NH per OH plus this is left NH per Cl 0.1 molar, this is 0.1 molar. Then we prepare the buffer solution. So condition is this has to be excess, so that after reactions also this has to be left, and you use these two and we prepare the buffer solutions. So these are the indirect way of preparing buffer solutions. So direct way is, this is the direct way of preparation of buffer solutions. So weak acid and salt, which is weak acid strong base, and weak base salt base strong acid. If this is present, then we can prepare the buffer solutions. And indirectly way, if that instead of salt they may give acids, then also we can prepare the buffer solutions. Or they may ask, like they wants to give that HCl, like they may give that NH per Cl they have given, and they have given HCl, then from here this will dissociate to NH per plus Cl minus. So they may give indirect way, give that NH per Cl plus HCl. So buffer solutions, is it possible? So what do that NH per Cl, what will do, give this is strong electrolytes, so this is completely dissociate NH per plus Cl minus. Why this is strong electrolyte? If any components comes from strong, then that will become strong electrolyte. So this NH per OH, so NH per come from NH per OH, so this is weak base, and this HCl, Cl has come from HCl. So since HCl is a strong component, so and this Cl comes from strong component, so NH per Cl is a strong component, so it completely dissociate. So in the solutions this is present, and HCl, this is also strong, so this is also going to give H plus Cl minus. So now what happened? So here we are not getting any weak components. This NH per weak components we are not getting, so we are not able to prepare the buffer solutions. Okay. So for buffer solutions, one is weak component, weak acid is needed, with that salt is needed, which is weak acid and weak base. Then only we prepare the buffer solutions. So these are the direct way they want to ask that here whether we can prepare buffer solutions or not. Okay, so we can solve it. So conditions you have to bring to these two states. If this states it's happen, then we can prepare the buffer solutions. And if this condition is not satisfied, then buffer solution will not prepare. Okay. Now how to calculate the pH of a buffer solutions? So next topic is calculations of pH of buffer solution. So let's say but we are having NH for suppose let's say for acidic buffer, let's say what we are having let's say CH3 COH weak acid plus we have any salt that is weak acid strong base. So let's say CH3 CO and A. Then here we can prepare the buffer solution. So how to calculate the pH of the solution? So since CH3COH is in the solutions, so see in our solutions these things is present CH3COH and CH3CONA, and whenever in the solutions it will going to give completely this is partial dissociate. This weak acid partially dissociate CH3CO minus plus H plus, and that this is weak, so this comes from strong component, so this is because strong electrolyte, so this is going to completely dissociate. Na plus. So in the components we are having CH3 COH is present, CH3 CO minus is present, H plus is present, and Na plus is present. Okay. So now let's say if it's time t0 initially, suppose this is C molar, then this is now has happened, and whenever t equal to t equilibrium, let's say C alpha is dissociate, then C minus C alpha. But whenever they see 0 0 t equal to 0 and t equal to t equilibrium, this is completely dissociate, then this is going to be CC. Okay, this is what happened. Yes. So now we are going to calculate the buffer solutions. So for buffer solutions, so let me write this. This is acid, right? So we can write Ka. K equilibrium constant is Ka, because for acid we use Ka. Then concentration of product by concentration of reactants. Yes, or I can put here the values so that it will clearly understood. So instead of that, let me put the value. So if I say this is 0.2 molar, you given 0 0, and from here only 5% per weak kilotolite, only less than 5% will dissociate, nearly or less than 5% dissociate. So let's say dissociate is 0.01. So this will be left as 0.199. So very less amount will dissociate, H plus and Cn minus. And if it is 0.2 molar 0 then from here it will completely dissociate because strong electrolyte. So 0.2 molar. Okay. And whenever it dissociate, then that we see this value is here 0.01 molar, and from strong electrolyte also the same value is there. So this is common. That is what the applications of common and effect, that same anions is present, and but this is very low concentration, but this is high concentration value is there. Okay, and this is, and what it says that Lee Chatter's principle, what it says that Lee Chatter's principle, what it says that if concentration of product increases, then backward shift, and concentration of reactants increases, then forward shifts will occur. This is the Lee Chatter's principle. Okay, so now what happened that uh, here, so CH3COH, CH3CO minus, so here, and whenever you are adding that common negative ions, you already discussed, whenever this is dissociate into CH3CO H plus, and in the solution CH3CO minus is present, and since this is a strong electrolyte, so it is completely dissociate. So this CH3CO minus high concentration is there. So if the concentration of weak electrolytes, if the concentration of reactants is increases, then forward shifts will occur, and if concentration of product increases, then backward shifts occur. So CH3CO minus is increases in the solutions due to the strong electrolytes, because this completely dissociates. So this value is increasing in the solutions, means this backward shifts occur. So the dissociations, whatever it giving 0.01, 0.01, this also nearly going to become very less, very less value, because of these concentrations due to the strong electrolytes and the common ions effect. uh, this concentration is increases, means concentrations of product is increases. If concentration of product increases, then the backward shifts will occur. So this value will be decreases more, and this value become nearly equal to 0.2 molar. Okay, so that's why what we says that whenever I say K equal to CH3CO minus H plus and CH3COH, so this value CH3CO minus, what happened that this value, see this value is very huge and this value is very less. So this value is generally used put from this, from strong electrolytes. Okay, because whatever it will completely dissociate at equilibrium. So only this value is present in the solution. So this is completely dissociate, so this value is there. So this value is generally put that whatever given the concentrations of strong electrolyte, because this completely dissociate into this and this. Okay, and H plus concentrations we can put from here, and CH3COH means this is like very less dissociate due to common ion effect. So this CH3COH acid concentration we can put the initial concentration, because this is very less dissociate, means that is nearly we can say not dissociate, so we can put that initial concentration of acid. Now this is the value. So now how we calculate the pH? So how we calculate the pH of the buffer solutions? So we know that pH equal to minus log of H plus concentration. Yes, so here I can write this H plus is there, so I can take this H plus. So from here I can calculate the pH. So what I do that Ka, I can multiply this into CH3COH. Okay, and this will get divided CH3CO minus that is equal to H plus concentration. Okay, or I can say H plus concentrations equal to Ka into CH3COOH CH3CO minus. No, so because pH equal to minus log of H plus concentration, so I want to get that pH. So what I will do, I will put both side minus log, or I can write simply taking, or sorry, multiplying minus log on both sides. What I'll do, so put minus log minus log H plus concentration. So here also I can put minus log, that is Ka CH3COH CH3CO minus. Okay, so what I do, minus log H plus concentration, then this is going to give minus log Ka, since we know that minus log A into B, that log A B, we can write that is log A plus log B. Okay, so since this is multiplied Ka, so I can write log Ka. Let me write minus in the common, so log Ka, this is multiplied, so Ka plus log CH3COH and also here I write log AB equal to log A into log B. Another log A by B, that is equal to log A minus log B. Okay, so here this is multiplied, that's why I like plus and minus, and this is divided, so what I put minus log minus log CH3CO minus. Okay, now both the cases, now here minus log H plus concentration, so both the cases minus is there, so this is become minus log Ka, and this is become minus log of CH3COH, minus minus become plus log of CH3CO minus. Okay, and we know that log A minus log B, they also can written as log A by B. So what I write, that minus log H plus concentrations equal to, this is minus log Ka, so this is, this I can write plus log minus because this is equal to this, so that's why I write like this. And we know that because pH equal to minus log of H plus concentration and pK equal to minus log of Ka, so from here I can write that this is equal to pH equal to this, I can write pKa plus log CH3CO minus CH3COH. Yes, so this is the formula to calculate the pH of a buffer solution. Now I can also simplify it, that pH equal to pK plus log, that is salt, because this is CH3CO minus each maximum comes from this electrolyte, because this is very high value and this is very low as prepared, so we neglect it mainly and we assume this value. So I can write here this CH3CO minus, I can write salt concentrations, and due to common ion effect, so this concentration is increases nearly equal 0.2 molars, because the forward shifts occurring, and this is high value means nearly that is not dissociate. So it is better to put that acid instead of this value. I can put that acid concentration, that is CH3CO concentration, so should put 0.19, but since this is nearly the initial value, so I will put the initial value. Due to common ion repeat, this is going to give the backward shifts, and this is high amount of value, and this will nearly not dissociate. So instead of this value, I can put that acid concentration, initial concentration of acid. So this value is put the put from the salt concentration, and this value is put this value is initial concentration of acid. So this is the generally, okay. So generally this is followed, and if that so generally if not given anything, then take that CH3CO minus, put the concentration of salt, and this will put the initial concentration of acid. But if that is mentioned, that suppose he says that let's say if it says that the question is given like CH3COH, that is going to give CH3CO minus plus H plus, and what is say that equal to 0. Now this is that says that 0.1 molar concentration, 0, let's say 0.2 molar, or let's say 0.4 molar, and T equal to T equilibrium, let's say this is very less value, so let's say 0. Let's say this is 1 molar, and this is dissociate nearly less than 5%, so let's say 0.5 molar, this is 0.5 molar, and let's say so not 0.5 molar, that is 0.5 molar, 0.05 molar, and let's say this is nearly equal to 0.95 molar. And if that is says that strong electrolyte, that is given CH3COO and A, and here what time they take that this is going to give CH3CO minus plus and A plus. T equal to 0. Let's say this concentration given 0.5 molar. So if the strong molecule given that very less concentration value of this value is given, then 0 0 and T equal to T equilibrium, this is going to become 0. Or let's say this value 0.07 concentration. So this is going to give 0. So this is going to give 0 and this is 0.07, 0.07. So now since these strong electrolytes, they given that concentration is very less, and if it is concentration is very high and keep the very low, it dissociate very less because this is weak acid, although this value and this value are nearly comparable. So on that case we can't take the CH3CO minus only this value because this value also comparable with this. So on that case we have to take this value also. So on that case, whenever write pH for this, then pK plus log, we will not write salt, we will not write acid. Here this is not valid. Here we have to write pH equal to pK plus log, you have to write salt, CH3CO minus not salt, and you have to write CH3COH. So here this CH3CO minus value is come from both here. So one is 0.07 plus 0.05. That value will come 0.12. So this value will come not 0.07. So we have to add for this case if the any that strong electrolytes or that salt, it is very low concentration given. On that case we have to consider that concentration of this value also we have to consider on that case. And here also CH3COH, so this is how much, 0.95 molar. On that case this is fine, okay. Or on that case we have also take this value, not that this value, we have to take this value because on that case this also can be considered. So if the strong electrolyte, the concentration is given very less, on that case this will not applicable, but 95% they will give this also high concentrations value, they will give this also the same equilibrium value. On that case we can use this formula, okay. This is how we will calculate the pH of the solutions. So next that we will discuss the working of the buffer solution. Next topic is working of buffer solution. Working of buffer solutions. So how, like if we add little amount of acid or base, pH of solutions will remain nearly unchanged. So how this is happening, that's what we are going to look now. So if you add little amount of acid or base, then why the pH of the solutions will remain nearly unchanged? Okay, so that's what called the pH buffer. Buffer means if you add little amount of acid or base to the solution, then the solutions of then the pH of the solutions will remain unchanged. That's called buffer solution. So now we are looking that how it is working. Why, if you add little amount of acid or base, the pH of that solution is not changing if the solution is buffer. So that regions, the answers we are going to understand now. Okay, so buffer means weak acid plus weak acid and strong base, that salt is there, so then that is going to give the buffer solution. So now we are we try to understand that what is there in the solution, so that if you add little amount of acid and base, the pH of the solution is not changing. What is the reason behind this? Okay, that's what we are going to understand now. So we know that buffers are two types, basic buffer and acidic buffer. So if we say that acidic buffer means that is acidic, like preparation is using acidic, like weak acid and weak base. Okay, and if what basic buffer means that weak base, from that weak base and strong acid, that is basic buffer. But solution is not buffer, but then we can say that is basic buffer because you use the basic, weak component as basic. This is acidic buffer, but this is not acidic, solution is not acidic, but we use that weak component acid, so that's why we call that acidic buffer. Okay, so buffer means that pH of that solution, pH of the solutions will remain unchanged, nearly unchanged. Okay, nearly unchanged. So now we'll look that acidic buffer. So working of acidic buffer. So if we add little amount of acid or base, acid means if we add little amount of acid means H plus we are adding, like if we say HCl, then that is going to give H plus and Cl minus. Okay, so you are considering only H plus, you are not considering Cl minus. Why? Because pH means that is minus logarithm of H plus concentration. So what is the H plus concentration? So if you add the H plus acid means you are indirectly giving H plus. So if you giving the H plus, then the concentration of H plus is increases, then what is the effect of the pH? And Cl minus, that is there, that will be react with other parts of the solutions, anions which is present in solutions of that pH solution, that will react, and we are not considering much more on it. We consider that this H plus concentration. After adding that HCl, that H plus going to these reactions and going to these solutions, and what is doing to this H plus concentration. After that, if H plus concentration increases, then what is the pH? H plus concentration is decreases, then what is the pH? So we look on it. So what is that? Suppose so for acidic buffer, weak acid plus weak acid, strong base. Okay, sorry. So weak acid means, let's say CH3COH, or you can say H, any organic acid, HCOH, any organic acid you can take. So I'm taking this weak acid, and that weak acid strong base, that is CH3CO and A. Okay, so whenever it react Then this will form the buffer solutions. So if I say in the solution, whenever I am reacting that CH3COH, then this CH3COH in solutions in water, what will give? It will partially dissociate into CH3CO minus plus H plus. Okay, and T equal to 0. Suppose this is, let's say, 0.2 molar. This is 0 0, and when T equal to T equilibrium, so it is dissociate very less amount. So let's say 0.01 molar, 0.01 molar. Then this is 0.199 molar. Okay. Similarly, we are having another component, that is this one. This is strong electrolytes. So this will completely dissociate CH3 CO and A, going to give CH3 CO minus plus Na plus. Okay, and when T equal to 0, let's say this is also 0.2 molar if taken, and when T equal to T equilibrium, so this is completely dissociate. So okay, so in the solutions, this is present, in the solution. Okay, so in solutions this is present, I mean solutions are CH3 COH is present, and this is also present, and this H plus is also present, and this is also present, so that I have already written, and this is also present, Na plus. Okay, so if you add, now what I'm doing, I'm adding the H plus, I'm adding the acid means H plus. Now little amount of acid, that is H plus, I am adding. So if I add little amount of H plus, then what it will go, it will react. So see, positive always react with negative. So this positive cations will react with negative anions. So this H plus will react with CH3 CO minus and will form CH3 COH. So what I write, this H plus will react with CH3 CO minus and you will give CH3 COH. So this, and another thing, that Lee-Chatter's principle, what it says, you will write Lee-Chatter's principle, what it says, that if concentration of reactants increases, then forward shifts occur, and concentration of product increases, then backward shifts occur. This is what given by the Lee-Chatter's principle. So what I'm doing, that CH3COH is increasing in the solution because H plus you are giving, that will react with CH3CO minus and CH3COH is forming. So this value, the concentration of this value is increasing, and if the concentrations of reactants increases, then forward shifts will occur. So this will do the forward shift. Okay, according to Lee-Chatter's principle. But the problem is, this concentration is already high because of this common ion effect, because this is a strong electrolyte, so this give the completely dissociate. See, this value is completely dissociate into this one and this one. So this value is very high, I mean this value is very high, I mean this value is very high it means that concentration of product is already very high. So according to that, concentration product is very high, then this should shift backward directions. And we remember that we add only little amount of acid, means H plus is very less we have added, means that is react with very less amount of CH3CO minus and form the CH3COH. But in our solutions this is present in a huge amount, 0.2 molar. Okay, so this will not go to the forward directions, it will not shift the forward direction due to common ion effect, because this concentration is already high, so it resists the forward shift. So although H plus will react with CH3CO minus and form the CH3COH, because we are adding little amount of acid, means little amount of H plus is coming to the solutions, and this little amount of H plus will react with little amount of CH3CO minus and form little amount of CH3COH. And although this concentration of this reactants increases, and this wants to shift the forward directions, but that due to common ion effect or CH3CO minus already present in the solutions in a huge amount, so this will resist in the forward shift. So if it resists the forward shifts, then forward shift not occur, so the pH of the solutions will remain nearly same. That is the reasons the pH of the solutions will remain nearly same. But if the case is, if you add instead of little, if you add more amount of acid, means H plus is high, then what happened, that H plus is high, so more amount H plus is coming to these solutions, and this CH3CO minus, because this is strong electrolyte, so it give more amount of CH3CO minus, so H plus will react more amount of CH3CO minus. So CH3CO minus is decreases because H plus you are giving more, so more H plus is reacting more number of CH3CO minus, so this value is decreasing in this case. Now so this decreases and more amount of CH3CO minus is CH3COH acid is prepared. So if this concentration is increases very high amount and this amount is already used up, so now the forward shift will occur because this value is already consumed by if you are adding more amount of H plus. Okay, on that case this forward shift will occur and more number of H plus will created and the solutions become acidic. Vapor is it is no longer vapor, it converts from vapor to acidic if we add more number, if we add more H plus. But for vapor solutions we have to add little amount of H plus or little amount of acid and base, then a pH is not changing, then we called it as vapor solution. But if you add more so acid, then that vapor will be converted into acid. Okay, so this is the case if you add acid. Now if we add little amount of base, base means OH minus. Okay, so OH minus, this negative will react with positives, so here positive is H is there, so OH minus will react with H plus and form water. Yes, and yes, here Na is also there, so OH minus can also react with Na plus, but this will give NaOH, and this is strong electrolyte, so this again going to dissociate and give N plus and OH minus. So in the solution that is present in this solution, so we will not consider this and we consider it this, because water is amphoteric nature and it is generally considered as weak acid. Okay, so this will not give and this will give. So if you add little amount of base or OH minus, then what happens, this OH minus will react with H plus and it react with H plus. So if concentration of so due to water formation, OH minus is reacting with this H plus, so this H plus concentration which decreases. So if concentrations of product is decreases, then it will shift, the backward forward shift will occur. Okay, the forward shift will occur, but the CH3CO minus due to common ion effect, this is completely dissociated, this is strong electrolyte, so this high amount is there, so this forward shift again resist because this is very high amount is present. Okay, and again the condition is if you add more amount of OH minus, then what will happen? If you add more amount of base or OH minus, then more amount of H plus will be used. It means H plus concentrations is decreases more amount. So if it is decreases more amount, then what happened? That H plus concentration in the solutions will decreases, and it will try to shift the forward directions. So it will forward shift directions will happen, but these concentrations are going to give CH3CO minus and H plus concentration, but this concentration CH3CO minus concentrations is already high amount, so this resist again the forward shifts because this is already in a huge amount. So overall what happened, that H plus concentrations only decreases in the solutions if you add more amount of OH minus. So it means that it will change into basic solutions. So from buffer it will change to base. So if you add more amount of OH minus. So generally for conditions of buffer solution is that if you add little amount of acid or base, then the pH of the solution not change, that is called buffer solution. It is not valid if you add more amount of acid or more amount of base, then also the buffer solution is not change pH. That is not the condition. Condition is if you add little amount of acid or base to the solution, and if the solutions the pH is not change or remain nearly same, on that case that we call the buffer solutions. Okay. So this is the working of buffer solution. So next topic is salt hydrolysis. Next topic is salt hydrolysis. So salt means, you know, that salt like it will make from weak acid plus strong base, then we can get one salt, that is salt of weak acid and strong base. So that how we get the salt. Let's say if I take that, let's say if I take any salts, sorry for the interruptions, my pen each get problems, so a minute I will check it. Sorry for the interruption. So salt hydrolysis. Okay. Salt hydrolysis. We were discussing. Salt hydrolysis. So what is that? Salt means that is salt. So that is prepared from any says any weak acid and strong base. Salt. So salt. Okay. So salt means salt is prepared from let's say salt means let's say an acid plus base, then we know it is going to prepare salt plus water. Okay, so if I search any acids, then if I say that HCl plus NaOH, then you are going to give any salt plus water. Okay, so this is the salt. So now we are going to understand that if you salt plus if you add salt hydrolysis means what? Salt hydrolysis means this is the salt and salt hydrolysis. Salt hydrolysis means ions of salt react with ions of water. Okay, ions of salts react with ions of water and ions of water and give some product, then that is called salt hydrolysis. Okay, so salts can be prepared from, like if we say that weak acid plus let's say strong acid plus strong base, then salt is going to give strong acid is strong base salts. If I say the example like HCl going to give prepare with NaOH, then that is going to give NaCl plus water. Yes, this is the salt. Another case, salt can be prepared from a weak acid plus strong base, then that is going to give weak acid, strong base salts. Example, if you said CH3COH plus NaOH, that is going to give CH3CONA salt plus water. So another others, like if you said that weak base plus strong acid, then that is going to be weak base, strong acid, salt plus water. So this maybe you can take NH per OH, strong acid, let's say HCl. I'm going to give NH per Cl plus water. Okay. Another you can say that weak base plus weak acid, that is going to give weak base plus weak acid, sorry, weak, that is weak base, weak acid, salt plus water. And this salt hydrolysis, the ions of salt react with ions of water. This will be very good reactions will happen when we have that weak components is high. So here weak components is not there, both are strong components, both are strong neutrals, so this will not give the salt hydrolysis. This will not give salt hydrolysis, because all are strong components for salt hydrolysis. Any one component needed to be weak, so both are strong, so this will not give the salt hydrolysis. So this will give the salt hydrolysis. This will give salt hydrolysis because weak components is there, and this also give weak hydrolysis, weak components is there. So I will discuss one by one, and why this will not give salt hydrolysis I will discuss now. We'll see. If strong acid plus strong base is there, then that is strong acid, strong base, salt plus water is prepared. Let's say strong acid, let's say HCl plus NaOH will react with NaCl plus water. And when this salt is prepared, and with salt hydrolysis means salt hydrolysis means reactions of ions of salt with ions of water. Okay, so here, so ions of salt NaCl, what Na plus Cl minus is there, and for water that is H plus and OH minus is there. So whenever you react the ions of salt react with ions of water means whenever I say NaCl plus water, so this will react. So let's say this positive part react with negative part, so let's say Na will react with this part NaOH, and this part react with this HCl. But this is happening in the solution, right? But the problem is in the solutions what we have, whenever react then this solution, that this again going to, this is strong electrolytes again going to give Na plus and OH minus. This is also strong, so again it is going to give H plus plus Cl minus. So in the solutions they are actually in the present in the ions forms, they will not react. If they react, again they are going to give dissociate, because they are actually strong electrolyte, and strong electrolyte characteristic is they completely dissociate. So that's the reasons that the if both the strong components are there, then the hydrolysis will not happen. Okay. So second case, if we have that weak acid plus strong base, then salt will become weak acid, strong base salts. Example, if we say CH3COH plus NaOH, then that is going to give CH3CO Na plus water. Now this is the salt, so this salt will react with water, so CH3CO Na plus water. So this is present as CH3CO minus plus Na plus, and this is present as H plus and OH minus. So whenever you react it, then these anions will react with H plus, because negative reacted to positive. So what happens? CH3 COH will form, and another is NaOH H form. Yes. And since this is weak acids, and whenever this weak acid will form, and whenever it will dissociate, then this is very less amount it will dissociate, and more amount is in this form. So this is dissociate into CH3CO minus plus H plus, but this dissociation to this ions is very less, because this is weak electrolyte, this is weak acid, and very huge amount of this form is there. Suppose this is 0.2 molar, and this is 0.0, and this is present 1.99, this is present 0.01, 0.01. So very less amount will this, means maximum amount this amount will be present here. And if we talk about NaOH, then this is strong electrolyte, so in solution this again going to dissociate into plus plus OH minus. So in solution, what it says in solutions, that we are having CH3COH, and we are having CH3CO minus is also there, and H plus is also there, and Na plus is also there, and OH minus also there. So in solutions we get that these components, and this NaOH is not present because they are again going to dissociate. So salt hydrolysis, what we are getting, that in salt hydrolysis the weak components of that salt will react with water. So weak components of the salt is salt is what? CH3CONa. This is the salt, right? Whenever you say that weak acid plus strong base, that's going to give weak acid strong base. So weak acid, you take that CH3COH plus NaOH, and that is going to give CH3CONa plus water. This is the salt. So from here the weak component is this acidic portion which come from here, so that is CH3CO minus, and this Na has come from this, which is strong acid, strong base. So this weak component of this salt will react with water. That is in salt hydrolysis, weak components of the salt will react with water. So weak component is CH3CO minus react with water, and that is going to give what? CH3COH plus OH minus, because this is H plus is present and OH minus is there. From here we are getting, in CH3CO minus react with H plus, and OH minus will left as it is. Now T equal to 0, let's say this is C molar is there, then this 0 0, and when T equal to T equilibrium, then let's say this is, so for hydrolysis we are taking as H, and for dissociation we are taking alpha. So in hydrolysis you will take H, not alpha. So I will take CH, CH, this is C minus CH. Okay, so now if we write that equilibrium constant, so equilibrium constant we write here, since this is hydrolysis, so we write H, so that is equal to CH, CH, C minus CH. So this value will be C CH square, C 1 minus H. So this will cancel, and this is, so this hydrolysis, this like alpha is very less compared to 1 minus alpha, this is very less, so we consider as 1. So this hydrolysis, this H will is also very less, so we consider as 1. So C H square H equal to CH square. So whenever H square equal to KH by C, and H equal to KH by C whole root over of. Okay, this is the value of H. Now we will calculate the H plus concentrations, and what we know that Kw equal to H plus concentrations and OH minus concentrations we already discussed. And what we write that here, this is for hydrolysis, we have also acid. So if we write CH3COH, whenever this is going to give dissociation, then that is going to give CH3CO minus plus H plus. So at T equal to 0, it is suppose C, then 0 0, and T equal to T equilibrium, then this is C alpha, then this is C minus C alpha. But now it's Ka, if you calculate, then that is going to give CH3 CO minus, and going to give H plus, and CH3 H. Similarly, if you calculate simply KH from here, then what is that concentration? That is CH3 COH OH and CH3 CO minus. Because this water is actually taken excess, so we will take, that is unit 1, so we will not take. So KH equal to this, and if you multiplied KH into Ka, then what we will get? So KH value is CH3 KH value is CH3 COH and OH, it is CH3 CO minus, and Ka value is CH3 CO minus H plus CH3 COH. So if I look it, then this value is cancelled, this value is cancelled, so remaining this value. So what I say, KH and Ka equal to H plus OH minus this and H plus, and what you know that Kw equal to H plus concentration into H minus concentration. So instead of H plus OH concentration, I can put here KH into Ka equal to Kw, because Kw equal to H plus and OH minus concentration. Yes. So this value, I can put this value. So I put this. So I got that KH into K equal to Kw. So from here, what I say that KH into Ka equal to Kw, and Kw equal to H plus and OH minus. So now I want to calculate the H plus concentration. So from here I can calculate the H plus concentration. So what I will do, this H plus concentration equal to Kw and OH minus concentration. This OH minus concentration I can take from this hydrolysis. So always take this OH minus concentration or H plus concentration. This value is always calculated from salt hydrolysis, not from acid. So this OH concentration or H plus concentration never take from acid part, because we are calculating the hydrolysis. So we always take this value from here. Okay, so here H plus we have H plus concentration I am having, but I am calculating here for the salt hydrolysis. So I will not take H plus concentration from here, because acid part will not take this H plus concentration. The concentration will take, since you are calculating for hydrolysis, so we will take only from here. Okay, so here I am having the OH minus concentration. So I will put this value, that H plus concentrations equal to Kw and OH concentration is CH. So I put here CH. Okay, and also this H value, I know that H value is KH by C. Okay, I will put that. Before that I will like to put also KW. Okay, so KW C, H value I know, that is KH by C, KH by C whole root over of this is H plus concentration. So now what is that? So if we will solve it, then see, this is this cancelled, and that is KW, that will be C, KH root over will come. Yes, sorry, this will come KHC root over of this value will come. Yes, so if K double and if KH will not given, this is the value of H plus concentrations, and if KH value is not given and Ka value is given, then we can do that. But no, KH into Ka equal to Kw. Yes, KH into Ka equal to Kw. So I can put that KH equal to Kw by Ka. So H plus concentrations will be equal to, so Kw, so Kh value is Kw Ka, and this is C whole root over of. Okay, now what will happen that, so if we will do that, then this will go up, then Kw into Ka by C whole concentration. So if we solve it, then we will get this value, that is C. Kw is there and Kw is there, so if you take this, then it reciprocal, then this will come Ka and C is there, and Kw we are half, this is 2 half Kw, so this will cancel and this will cancel lower part, so only Kw is left into Ka and concentration whole by root over. Okay, simply mathematics will do, then you will get this value. And this is for if you have the weak acids, weak acid and strong bases there, then you will find the H plus concentration like this. And now if you have, now third part is, if you have the weak base plus weak base strong acid, and then sorry what I'm going to do. So now you have that salt which is weak base strong acid salt plus water, then how will you prepare? So we have weak acid, that is NH4OH, plus if you react with any strong acid, let's say HCl, then that is going to give NH4Cl salt plus water. And whenever this salt, this is salt of that is weak base strong acid, and when this salt NH4Cl will react with water, then what happens, this will give the salt hydrolysis. So what will do that, so this is actually H plus and OH minus is present. So what happened is, this is going to, this is strong electrolyte because this comes from strong acid, so this is actually NH4 plus and Cl minus is there, so this will react with this, so positive will react with negative, so this will form NH4OH and HCl. Okay, but thing is that this is weak acid and this is strong as this is weak base and this is strong acid. So in the solutions, if we have the solutions, sorry, in the solutions, so in the solution, whenever this is actually NH4OH, NH4OH, this will be very less dissociated and very much amount, this amount is there, so NH4 plus and OH minus, because this is base but less dissociate. So if we say this is 0.2 molar, 0 T equal to 0 and T equal to equilibrium, this is let's say 1.99, 0.01, 0.01, this amount, so very less dissociate. So in the solutions this amount is present, and whenever you say HCl, then this is complete dissociate, H plus plus Cl minus. So in the solutions the HCl will not present, because T equal to 0, let's say 0.2 molar, 0, and T equal to T equilibrium. So this is completely dissociated. 0.2 molar, 0.2 molar. So this is not present in the solution. So H plus and Cl minus is present. So only this compound is forming in the salt hydrolysis. So in the solutions, only present is NH4 OH and present H plus Cl minus is present, and NH4 present but very less amount, and OH minus is present very less amount. So this is present in the solutions. So in salt hydrolysis, what we take the big components of the salt will taken. So this NH4 which comes from this weak base. So this is NH4 which come from this weak base. So this is the weak components of the salt. So our salt is which? Our salt is NH4Cl. So this NH4 is NH4 plus comes from NH4 plus is comes from but NH4 which is weak base. So weak components. So weak components will react with water for salt hydrolysis. Okay, for salt hydrolysis, weak component of salt react with water. Okay, so weak component is NH4 plus. So NH4 plus react with water, and that is going to give NH4 OH plus H plus concentration. So since this is weak, so it is better to write like this. Okay, so whenever T equal to 0, so let's say this is C 0 0 0, when say T equal to T equilibrium. So let's say C amount of this is formed, so C minus CH. Okay, so if we write that KH, then that is going to give CH C minus CH. Okay, so if you write this, then CH square C 1 minus H, then this will cancel. So KH equal to CH square, because this is nearly equal to 1. Okay, this is the KH value, and H equal to KH by C whole root over of this is the value of H. So we want to write that H plus concentration. So here H plus is already present. So from here, see, for H plus concentration or OH minus concentration, we will take from here only, or we will take from Kw equal to H plus concentrations and OH minus concentration. So H plus concentration, OH minus concentration, we will take either from here or from here. We will not take from acids. Note that our acid is also there, NH4OH. This is also going to give NH4 plus OH minus. So let's say it equal to 0. This is C 0, then C alpha, then C minus C alpha. So OH minus here also present, but we will not take OH minus concentrations from here. This is wrong. Okay, for hydrolysis, we have to take that OH minus concentrations either the salt hydrolysis components or for that Kw equal to H plus OH minus. So we will take either from here or from here. So we will not take from these acids because we are talking here hydrolysis. Here we are talking about of H, not alpha. Okay. So H plus concentration is already present here. So we need the H plus concentration that is equal to CH, and H value we know that is KH by C. So C KH by C whole root over of, and so if we multiplied it, then this will remain as KH C whole root of, that is H plus concentrations, and we know that because KH into, here that weak component is base, so here weak component will come into KW. Okay, so whatever the weak component is there, if you multiply with KH, then you will get KW. If both are weak component, then like if both are weak component, acid is also there and base is there, then we have to get this like this. So whatever the weak component, if you multiply with KH, then you will get KW. Okay, so here weak component is KB, so KH into KB equal to KW. Okay, so here from here, so KH equal to KW by KB. So just put that H plus equal to KH equal this, so KW into C by KB equal to this. So this is the H plus concentrations if the weak component is basic. Okay, so summary, if I say if weak acid and strong base salt is there, then H plus concentrations is that is equal to, what the value, KW into Ka into C. So KW into Ka by C whole root over of, and if weak base and strong acid, then H plus concentrations is KW into C by Kb whole root over of. So this is the H plus concentrations for this salt hydrolysis. Okay, now next type is if both are weak acids. Next type is if both weak acid and weak base salt is like that. I mean CH3 COH, this is weak acid, that is react with weak base, let's say it's NH4 OH, then the salt will pour, that is CH3 COO NH4 plus because here just a minute. So this is actually this is CH3 CO minus and H plus is there, and this is NH4 plus and OH minus is there, so this negative will react with positive CH plus, and this will react with this, so this will form the water. So here the weak components are both, this is also come from weak component, this also come from weak component, and salt hydrolysis will, water will react with weak components. So now that CH3COO minus, or I can write CH3CO minus and NH4 plus react with water. So that will give what? CH3 COH plus that will give NH4 OH. Okay. So these weak components are both this and this, both are coming from weak components because both are weak acid and weak base. So if I say T equal to 0, let's say if I take C, this also I take C, then this is 0, 0. If I say T equal to T equilibrium, let's say C H amount is get this value, then this is C minus CH, C minus CH. So now the thing is that if you calculate that KH value, then that is this value. You have to calculate. So that is CH concentration of product, C minus CH, C minus CH. This value you have to calculate. Okay, so this gets CH value. So what is this value? Will get KH equal to CH C 1 minus H, this is C 1 minus H. So this value cancel, this value cancel, and this is nearly equal to 1, this is nearly equal to 1. So KH equal to H square. So H equal to KH by whole root over of this value we will get. So we will calculate that H plus concentrations. Okay, so I will calculate H plus concentration. So here KH equal to Ka, because both are coming from weak component of acid and weak component base, that is equal to Kw. Another also we know that Kw equal to H plus concentration and OH minus concentrations. But problem is that H, and if I write that H plus concentrations here, then that is equal to Kw and OH minus concentrations. But problem is that here nowhere is there OH minus concentration is not there. OH minus concentration not given here. So what we will do? We will use the reactions. So here we will not do that. We will not do like this. We will not do like if you do that CH3 COH, this is there. Okay, this is going to give CH3CO minus plus H plus. So what I do, taking T equal to 0, so C 0 0, T equal to T equilibrium, so C alpha C minus C alpha. So you will not do like this. Okay, so or CH C minus CH, this is 100% wrong, because here we are talking about acid means alpha will come, not H. And if alpha will come, and this value will not used in salt hydrolysis. Okay, so you will not use H plus concentration from here. This is wrong concepts. So I will calculate that H plus concentrations. So what we'll do that, okay, we'll get up to this value. So what we know that this CH3COH is there, then that will dissociate into CH3CO minus plus H plus. This will dissociate like this, and NH for OH is there, that is going to dissociate into NH for plus OH minus. So here if you write that Ka below, then what will get that CH3CO minus H plus by CH3COH, you will get this one. And here if we write that Kv value, then we will get NH4 plus OH minus, and we will get NH4 OH. Okay, so can I put from here, can I get the H plus concentration? Yes, we are not using the concentration value, we are just going to use the cable. So from here we can use the K H plus concentration. So this is no need, because H plus is directly we have from here, so I can use this value. So from here that H plus concentrations equal to Ka into CH3COH and by CH3CO minus. Okay, so H plus concentrations is Ka into CH3COH CH3CO minus. Okay, it's fine. Then from where, so this value we will get from here, right? CH3COH value is there. CH3COH value is Ka into CH3CO value is CH, and CH3CO minus is value also you know, that is C minus CH. So C minus CH. Okay, so now so you use the concentrations value only from the salt hydrolysis. So this value is comes from here and here. Okay, so we only use the concentration value from that only, we not use the acid concentrations value. So this value you get. So what I'll do, this is equal to Ka into CH, this is C 1 minus H, so this will cancel. So H plus concentration is equal to Ka into H, so this is nearly equal to 1, so 1. So H plus concentration is equal to Ka into H, and H equal to you know root over of Kh, so that is Ka to root over of H, and sorry, root over of Kh, and Kh into Ka into Kb equal to Kw. So here Kh equal to Kw by Ka into Kb. So just put the value Ka root over of Kw Ka into Kb. So if you notice it, this and this, then this will cancel off, then Ka into Kw by Kb. This is the H plus concentrations for if you have both weak electrolytes. Okay, so 3 cases we get that if, so third case is if both are weak acid and weak base, then H plus concentration is equal to Kw into Ka by Kb. So these are the H plus concentration. This way we can calculate the H plus concentrations. For this class, after this, thank you.